So hello everyone, and it's Richardson here in Sun Science here again. Okay, so today our topic for discussion will be a very important concept in organic chemistry, that is your pericyclic reactions. Okay, so generally this pericyclic reaction is very important for you to prepare either in your research aspects or when you prepare for your competitive exams and etc. Okay, so today we will discuss the first part of the pericyclic reaction. So there are many types. I'll be discussing about the electrocyclic reactions in brief today. Okay, so before going to that, I would like to recommend a book, a very good book which you can refer for pericyclic reaction, that is Sunil Kumar, Vinod Kumar and SP Singh, Pericyclic Reaction, a mechanistic and problem solving approach. So this book covers a very clear idea about the pericyclic reaction with a lot of examples which are more relevant for to get you prepared for the competitive exams. Okay, so let's get into it. So you know that normally pericyclic reactions are reactions which involve only heat or light. Okay, so the reactions are induced either by heat or light. That is a special role for your pericyclic reaction. Okay, we need to understand some properties of the pericyclic reaction which gives a unique identity to the to the organic reactions. Okay, so the three properties are: one, there is no intermediate formed in the pericyclic reaction. So normally in your organic reactions you see some intermediates like carbocation, carbanion, carbenes, nitrines and etc. But in pericyclic reaction there are no such intermediates which is formed. Number one. Number two, the reaction proceeds through a cyclic transition state. So this you have to remember. So no intermediate is formed, but the reaction proceeds through a cyclic transition state. And number three, the reaction takes place via concerted mechanism. So the concerted word reminds you that it is a single step mechanism, that is bond formation and bond breaking will take place simultaneously. So these are some important properties, very unique properties of your pericyclic reaction which you should know. Okay, these are some of the types of pericyclic reactions. You have electrocyclic reactions, cycloaddition reactions, sigmatropic reactions, chelotropic reactions and group transfer reactions. So for today we will discuss about the electrocyclic reactions. Okay, so in later videos I'll cover all these types of reactions. Okay, so before that, what we need to know and what are the things you need to understand to get a good idea about your pericyclic reaction. Three things you should know. One, you should know to draw pi molecular orbitals, or you can call it as your orbital lobes. And number two, you need the idea about HOMO and LUMO. You know that HOMO is the highest occupied molecular orbital and LUMO is your lowest unoccupied molecular orbital, where LUMO has highest energy than your HOMO. And then you need to know the idea of node. We know that what is a node. So generally we define node as the probability of finding electron is 0. So you cannot find an electron in that particular place. But here when you draw a pi molecular orbital, I can call node as the point around which, the center of point around which the orbitals are different. So how can I say that? So let's go to discuss how to draw the pi molecular orbitals. Okay, so for example I take my ethylene molecule. Okay, this is your ethylene and you know that you have one pi bond. So one pi bond means two electrons, so you have two orbitals, right? You will be drawing like this, two psi 1 and psi 2. You will get like this, psi 1 and psi 2, right? So now see here there are two carbons, so you can see that the pz orbital of this carbon and pz orbital of another carbon. So I draw like this. So for psi 1, first this is 1, I consider this as n. To know the number of nodes you just do n minus 1. 1 minus 1 is 0, so no node. So what I defined, node is the point around which the orbitals are different. But here the orbitals are not different, they are same. See here it is plus and here it is plus, so you will not get a node. But see here psi 2, that is 2 minus 1, you get one node, and you can see that the point around which the orbitals are different. See here it is plus and here it is minus, and you can say that you have one node. See, the point around which the orbitals are different, as different symmetry. That's it. Okay, and you can see that you have the HOMO and LUMO, which has been shown here. You just divide it equally in the bottom and the top, and you can see the ground state and excited state shown. So ground state corresponds to your thermal condition. Okay, I told you pericyclic involves thermal and photochemical reaction. So the ground state corresponds to your thermal and the excited state corresponds to your photochemical condition. Okay, so in the ground state, the HOMO is this. Okay, for thermal condition, your HOMO is for the ground state, and under photochemical condition, you see it is excited, and this will be your HOMO. So you should remember that. Okay, okay, let's go for let's discuss for 1,3 butadiene. So ethylene is a simple molecule. So let me go with the other thing. 1,3 butadiene. Yeah, you see that you have 4 carbons, so there are 4 p orbitals involved. So I just draw 4 lobes, and you see 2 pi bonds are there. So 2 pi bonds stand for 4 electrons. So I am filling 4 electrons over here, and we have psi1, psi2, psi3 and psi4, since you have 4 carbons. So how many number of carbon, you just put that much of psi. Okay, psi1, psi2, psi3, psi4, because I have 4 over here. Okay, now I'll draw the lobes now. You see here, this is psi1, so no node. So all will have same symmetry. So plus, 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 plus. Orbitals are same. Then psi2, 2 minus 1, 1. So you will have one node. So you see for one node, you should not keep the point somewhere else. It should be symmetrical. So when you see how it is, it should be unique and it should be somehow symmetrical. Okay, you should not just put the points anywhere. Okay, now you see your one node, and here you have 2 nodes, and here you have 3 nodes. So this is how you draw your pi molecular orbitals. Okay, I'll tell you a trick how to remember your nodes, how to put the nodes, and how to identify what sign to put. Okay, I'll just tell you. Now it is psi1. You see that this one number is odd. Okay, if your psi is odd, what you do is, in the terminal lobes, okay, you just put same sign, plus and plus. I think you can get it, right? So if your psi is odd, in the terminal lobes, you put plus sign. See here, this psi1 is odd. In the terminal lobes, I put plus sign. And see here, psi3 is odd. In the terminal nodes, I put plus sign. This will help you to identify the node and put the signs properly. Okay. Now, next one. If your psi is even, in the terminal lobes, you put opposite sign, plus, and here it is minus. I think you can get it, right? So, in the terminal lobe, you put opposite signs. Okay, you see here, psi2 is even. In the terminal lobe, you see opposite sign. And see a psi4 even. In the terminal lobe, you put opposite sign, and this will help you to draw the pi molecular orbitals. This is one of the method. Okay. Okay, let me erase it. Okay. Now this is for 135 hexatriene. Okay, so it's also very simple. So you have 6 carbons in hexatriene. So I have 6 orbital, pi molecular orbitals drawn over here, psi1 to psi6, and you can divide it equally like this, and these will be a bonding molecular orbital, and the above part will be your anti-bonding molecular orbital. Yeah, okay. So now you see here the same condition. For psi1 is odd, so in the terminal will be plus, and psi2 is even. In terminal node you put plus and minus, opposite signs. And similarly you can do that n minus 1, and you find the number of nodes, and you can keep it, and accordingly you can put the signs. This is how. Okay, how to identify this HOMO and LUMO? Very simply. Okay, so suppose in some questions they are asking, find how many nodes are there for this particular compound. So you no need to draw the diagrams for everything, and you just check it. We have a trick for that. So very simple. What you do is just see the number of carbon. You know that hexatriene has 6 carbon, correct? So now what you have to do to find the HOMO, just do n by 2. Okay, for thermal condition. For thermal condition, you do n by 2. So we have 6 carbons here. So 6 by 2 is 3. 6 by 2 is equal to 3. And you see, psi3 is your HOMO. See, How you have found it? So to find the HOMO in thermal condition, you see, do the formula n by 2. N represents the number of carbon. So 6 by 2 is 3, and this is your HOMO. Psi 3 is your HOMO, and you will choose this orbital to solve the problem. Now, suppose for photochemical condition, okay, you just do n by 2 plus 1. That's it. See here, n by 2, we saw it is 3 here. So 3 plus 1 is 4, and you see psi 4 is your HOMO for this, and you choose this orbital. Right? So I think you can get it. Okay, so this is the formula you should remember. For thermal condition, to determine the HOMO, put n by 2, and for photochemical condition, put n by 2 plus 1. Okay, remember this, and you can find the HOMO easily. Okay, good. Now the next one. So this is the definition for node which I told you, the point around which the orbitals are different. So this is how you will draw your pi molecular orbitals. Okay, now let's get into the electrocyclic reactions. Okay. So these are some points to understand the definition for this. It is an intramolecular reaction, number 1. Okay, so it is an intramolecular reaction, and then you see it involves interconversion of a conjugated polyene and a cycloalkene. Conjugated polyene represents it has 2 or more double bonds. Okay, suppose if it has a two pi bonds, okay, that is a conjugated polyene, it will be converted into 1 sigma bond and 1 pi bond. That is, you are resulting in a cycloalkene, and then this will it is a reversible reaction. So again, conjugated polyene. So your electrocyclic reaction is intramolecular reaction, and it is a reversible reaction between a conjugated polyene and a cycloalkene. Okay, it is induced either by thermal or photochemical condition. So we have two conditions here, right? Thermal or photochemical. So I don't know which should be applied properly. Okay, so whether thermal condition will make this interconversion or photochemical will make this interconversion. Okay, I don't know. So for that we will move on to discuss about the frontier molecular orbital concept later. Okay, so this is an example of electrocyclic reaction. You can see here, right? So we have 2 pi bonds. It is a conjugated polyene, and see here the electrocyclization takes place. So the pi bonds, the pi electrons involve cyclization, and then you see under thermal or photochemical condition the product is formed. So I don't know which condition, so for that we have to discuss the FMO approach, then only you will understand. See here, 2 pi bonds is converted into 1 pi bond, and you have a new sigma bond formed over here, right? Good. Let's go the next point. Electrocyclic reactions are of 2 types. Okay, one is your ring opening and ring closing. In the ring opening, a pi bond is formed. In ring closing, a sigma bond is formed. You can see here, right? See, it is a ring closing. In ring closing, you can see sigma bond is formed. Okay, here a new bond is formed, right? But in ring opening, so when I try to open this ring again, see, if I do like this, you can see the sigma bond is broken and a pi bond is formed, correct? So 2 pi bond has become 3 pi bond. Here 3 has become 2. So this is 2 types of electrocyclic reaction. Okay, if you notice. And then the next thing, one more thing you have to notice is about the stereochemistry for the ring opening and ring closing. 2 types of rotation motions you have to understand properly. One is your con rotatory motion, and the other is your dis rotatory motion. Okay, so what is con and what is dis? I'll just give you very simple definition. In con rotatory, you have to rotate your atomic orbitals in the same direction. Okay, in pi molecular orbital we saw, no, these are the lobes. These lobes are to be rotated. Then only you will get the bond formation. You know how a bond will be formed, right? You can see the example here. See, when same signs are there, if the orbitals are having same symmetry with same sign, you can see that a bond can be formed. So this bond is formed by the combination of this orbital, atomic orbital, right? Which has the same sign. You have to notice that. So that's why we go for con and dis rotation. So con means you have to rotate the atomic orbital in the same direction, either towards the right, both the lobes towards the right, or both the lobes towards the left. In dis rotatory motion, you can do it in opposite sides. So the arrow mark is shown here, right? You can do like that. Okay. Next, you have to notice the symmetry concepts. So two types of symmetry arises for this. One is your M symmetry and the other is your C2 symmetry. M stands for mirror. So that means when you rotate, you can see that your lobes are in mirror images. So plus minus means the other lobe also has plus and minus. That's it. C2 symmetry in the opposite signs will be same. Okay, that's the thing. So these are two types of symmetry, and let's discuss some example to understand this con and dis rotations. Okay, for example, I choose a ring opening of cyclobutadiene. Okay, ring opening of cyclobutadiene. You can see here, this is sorry, it's not cyclobutadiene, it's cyclobutene. Okay, it's a mistake here. So cyclobutene, I take it, and you see here, the ring opening has taken place like this, and it comes here and goes here, and you see that the ring is open. That's it. Okay, let's discuss now. You see that a sigma bond is present here, and that bond is broken, and a pi bond is formed over here. Correct. So how the sigma bond would have formed? When the orbitals is having same sign like this. So plus and plus, minus, minus, like this. In the terminal lobes, so actually the diagram will be like this, right? Okay, I'm not going to consider these one. Okay, I'm just taking this one because the sigma bond is breaking and forming the pi bond. Okay, no need to think about this one. So now you see this is bent and written according to my diagram. That's it. And you see here, when you rotate it towards the same side, the left side, I'm doing con now. Okay, con, you can see that the lobes have opened, and you see this plus is here and this plus is here and minus is here and minus is here, and it is a C2 symmetry, right? And then the same thing I did in left side. No, now I'm doing in right side. You see you have the con again, you're doing con, and see the plus plus, the lobes are rotated. See this minus has come here and this plus has come here. Okay, again you result in C2 symmetry. So you can understand that con you do either in right or left in the same direction, you result in C2 symmetry, right? So for con, the letter starts with C, so you remember that it is also C2. C, C2. Okay, always when you do con rotation, you result in C2 symmetry. Okay, you have to remember that one. Okay, now we have other example. We do dis rotation now. Dis means you do in opposite direction, right? So you see here, okay, it's like this, and you see the arrow marks are shown here, and dis rotation is done. You see it results in M symmetry. See dis rotation, this plus comes down and this plus also comes down. You see minus plus, and it is a mirror symmetry, right? The dis you can do in the other opposite direction also, inwards, and you can see again plus minus and plus minus, again M symmetry. So you have understood that always con will result in C2. So C, con results in C2. Your dis results in M symmetry. Okay, good. Now next, okay, this is what I told you. And now if suppose in your exams or in question papers you can find that they'll give some substituents to not be empty like this, right? So if they give any substituents, you should notice that the substituents will also rotate according to their rotation. So when you do con rotation, if you rotate in same direction, if your substituent is present attached to that carbon, that will also rotate. You have to remember that. In this rotation, if you do in opposite direction, to the same direction as your atomic orbital, your substituents will also rotate in that direction. Okay, you remember that. That's given here. This is very important point you have to notice. Let's go with some example. A ring opening. Okay, I have to identify whether con or dis has been done over here. Okay, you can see, you see the reactant and you see the product. Okay, either con or dis is done. You should tell that. You know that this sigma bond is broken here, right? Okay, here pi bond should come. Okay, the sigma bond is broken here. Okay, here it is not present. So how it has taken place? So this sigma bond can be like this. So plus and plus will be joined, and you see it is symmetry allowed, and a bond can be formed like this. Now, so the groups are attached like this. So I put it in the same way. Now what I am trying to do is, see here this methyl is at the top and now it is here. So what has happened? They have rotated like this. This methyl has come down. Okay, if I rotate like this only, this methyl will come down. And you see that this methyl has gone here. So what I have to do, I have to just move like this. So what happens? This methyl comes here. Oh, sorry. Like I have to move like this. And you see that this hydrogen has come here and this methyl will come here. Okay, so now you can get an idea, right? How to do it. You can see here. Okay, see this methyl to come down, if I rotate, my orbital is rotating minus and plus. See, the methyl has come here, the same place, and see, if I rotate like this, the hydrogen has come here and the methyl has come here, and your lobe is also shifted up, and see, your methyl is here. And you can see the symmetry, minus minus and plus plus. You did con rotation, right? If you do in same direction, it is con. So con means you get C2 symmetry, and see, it is C2 symmetry. Okay, so this is how you have to do it. Okay, let's go with one more example. Okay, we can try this one, right? So the same thing, this methyl is here and this methyl is in down. Now you see this methyl has come here. So when I do like this methyl will come here, and this methyl should come here. So how to do? I have to do like this, right? When I do like this methyl will come here. See, the top methyl has come here in the correct direction, and when I do like this methyl comes here. So I have done opposite direction. So this itself you can identify it as this, right? The answer is this rotation. Okay. Now we'll go with the ring closing, the same example. Okay, a pi bond should come, and you can see the methyl hydrogen is here, methyl hydrogen is here. I want to find whether it is con or dis. Very simple. You see this methyl is here and it should come at the top. So what you do? You just rotate like this. Correct. And this methyl is here, and what you do? You just rotate like this. See, same direction, you call it as con. The lobes are also shown here, and this example is also the same thing. You see, for ring closing only, con or dis, you can identify. This methyl is here, so I do like this, and this methyl is here, so what I should do? It should come here. Okay, so I should do like this. It is opposite rotation, and you call it as dis. Right? Very simple. Okay, now we are going to discuss about the FMO approach, that is the Frontier Molecular Orbital Method. Okay, so this is very important. So okay, whether your reaction is thermally allowed or photochemically allowed can be determined by knowing the FMO method. Okay, so FMO is a very simple approach when compared to your correlation diagram and PMO. Okay, that is a perturbation molecular orbital method. So why FMO is? FMO just takes the HOMO of the orbitals. Okay, it just take the HOMO of the reactant, and just with that itself you can examine whether it is a thermally allowed or photochemically allowed. See, this method is useful in quickly predicting whether a given pericyclic reaction is allowed by examining the symmetry of HOMO and LUMO. Only the HOMO and LUMO of the reactant is enough to determine whether the reaction is thermally allowed or photochemically allowed. Under thermal condition, your ground state is the HOMO. Under photochemical condition, your excited state is the HOMO. Okay, we know what is the excited state and which is the ground state and all, right? Okay, now the symmetries which we discussed earlier. So always C2 symmetry will give con and M symmetry will give dis. You remember like this, C2 means it's con. So these are some ideas you have to know. Okay, now let's go with the FMO approach, how to do it. Okay, the interconversion of butadiene to cyclobutene. Okay, so this is your butadiene. It is converted into cyclobutene. I don't know whether this reaction is induced thermally or photochemically. So if I want to induce it thermally, what type of rotation I should do? Either con or dis, I don't know. Either in photochemical, either con or dis is possible, I don't know. So this one can be answered by FMO. Now you see, first thing you have to notice is that 3 questions you have to ask. Number 1, you just check whether all the pi bonds are involved in cyclization. Number 1. Okay. After that only you have to analyze whether it is a 4n system or 4n plus 2 system. Okay. And then you go with the further discussion. Okay. Number 1, what you have to do? First identify whether all the pi bonds are involved in cyclization. Okay, I keep on telling this because in the later thing you will understand when we solve the problems. Okay, you have to understand very clearly. Now you see here, and this pi bond is shifting here and this pi bond is shifting here, and all the pi electrons are involved in cyclization. So totally there are 4 pi electrons, right? So it is a 4n system. It is a 4n pi electron system. Yeah, good. So the first thing you identified. So 4n system, and you see you will know to draw the pi molecular orbital lobes, and you know how to find the HOMO for this also. So in ground state, you know this is your HOMO. In excited state, this is your HOMO. To simplify, I said the formula. For thermal, it is n by 2. So n by 2 means butadiene has 4 carbons. So 4 by 2, 2. So Psi2 is the HOMO. right? For photochemical, n by 2 plus 1. So 2 plus 1, 3. So psi 3 is your HOMO. Okay, remember this for thermal condition and for photochemical condition. Okay, now let's discuss for thermal induced cyclization. Okay, so what is this thermal induced cyclization? You see here that this one goes here and comes here. This is how the cyclization takes place. Now I take the thermal condition. Okay, thermal condition, psi 2 is the HOMO. So I just draw the pi molecular orbital of the psi 2. Okay, see, so this is your psi 2. So I just take this one. Okay, I have drawn it. 2 is even, so plus and minus on the opposite side. And now what I do, I just try to do con rotation. Okay, I do con rotation. Con means on same side. See, I am doing on same side here. Same side. So what happens, this plus comes here and this plus comes here and a bond can be formed, and this is a symmetry allowed condition. Now I do this. This means opposite direction. See, I am doing this here, and you can see don't take this, not this lobes. Okay, I'm just doing with this lobes. And when you do this, this comes here. So minus comes here and the plus comes here. So what is happening? Minus and plus, they will not form bond, and it is symmetry forbidden. The same way now I will try for photochemical condition. So see, psi 3 is your HOMO. So I just take it and I do con. When I do con, see, same direction, you see plus and minus, symmetry forbidden. And when I do this rotation, you see this minus and this minus joins and you get symmetry allowed condition. So I can conclude like this. For 4n system, this is a 4n system, thermal and photochemical. Under thermal condition, con is allowed. I can write it as con, and under photochemical condition only this is allowed for 4n system. Correct? This is how you will understand it. Now, when I go for hexatriene 6 pi electron system, first question you have to understand whether all are involved in cyclization. Yes, all pi electrons are involved. So totally 6 pi electrons. It is a 4n plus 2 pi electron system. Correct? So the same pi molecular orbital diagrams you will be drawing. This is your HOMO. So 6 by 2, 3 HOMO, and 6 by 2 plus 1, that is 4. This is your HOMO for photochemical condition. That's it. Now I'll try for thermal condition. See, I have drawn it. Okay. And you see, for when I do con, it is symmetry forbidden. Plus will come here and minus will come here, and you see it is symmetry forbidden. But when I do this, it is possible. See, when I do in opposite direction, this minus and minus combines and it is symmetry allowed condition. Correct? This is how you do. And so in 4n plus 2, for thermal condition, this is allowed. Right? But photochemical condition, you see here, when I do con, it is allowed. So when I do con rotation, plus and plus joins and it is allowed. But when I do this, it is symmetry forbidden. So as a whole, we can tabulate it very simply, which was tabulated by Woodward-Hoffmann. We call it as Woodward-Hoffmann rule. Okay, it is the selection rule for your electrocyclic reaction. For 4n systems, we saw for thermal condition it is con, and for photochemical condition it is dis. And in 4n plus 2 system, for thermal it is dis, and for photochemical it is con. See how easy it is. So when you remember this table very clearly, very easily, then you can do many problems. So these are some tricks which we discussed, right? So if it is odd in terminal lobe, you put same sign. If even in terminal lobe, you put opposite sign. Then to find HOMO, okay, in thermal condition it is n by 2. N represents number of carbon. In photochemical, n by 2 plus 1. So n is number of carbon again, and you get the plus 1, that is your HOMO for photochemical condition. So the example is worked out here. Okay, so in the next video we will discuss some problems related to electrocyclic ring closure. Okay, and some more detailed concepts, how to solve some stereochemical questions in your exams. Okay.